Hello everyone, welcome back. Machine learning is reshaping cybersecurity and we are exploring it from every angle, from threat intelligence detection to AI driven teaming. Let's begin. Before we train any machine learning model, before we write a single line of code, we need to answer one simple question: what exactly is spam? What exactly is ham? Now, most of the people have seen the spam email and unwanted messages flooding into your inbox trying to sell you something, scam you, or worse. By the term ham is what we call legitimate, safe emails, the one you actually wanted to receive. Think of it as a simple two bucket system. Email in a world fall into two categories: ham or spam, and our machine learning model, their entire job is to decide which bucket each email belong to. That's it, simple concept but powerful execution. Take a look at this inbox right here. I have got a sample of email, just their subjects, and on the right the prediction ham or spam. You will notice email like your meeting is confirmed for 3 p.m. or project update for the team. Those are clear ham, legitimate, expected, nothing suspicious. But then look at this: win a free iPhone now. Click here to claim your prize. Those scream spam. Even without a model, your brain already flagged them. That's instinct you just had. That's exactly what we are going to teach our machine learning model to do, but consistently at scale across thousands of email per second. So, what makes spam look like a spam? They often make unrealistic promises: free money, prize, miracle cures. They target your emotions, excitement, fear, urgency to push you click without thinking. On the other hand, is contextual, specific, and expected. It comes from someone you know, reference something real, or uses normal, calm language. These patterns, these real world signals, are exactly what machine learning model learn and detect. And we are going to walk you through precisely how that works, starting with the simplest building block number. Now, here is where it gets interesting, and this animation is going to make it crystal clear. Look at the email subject: buy cheap drug now. Watch, we highlight buy, the model assign the weight of 2, we highlight drug, the model assign a weight of 3. Now we calculate. So we have this formula: y equal to 2b plus 3d, that give us the value of 2 plus 3 5. If our threshold says anything above 4 is a spam, this email is instantly classified as a spam. No guesswork, pure math. This is the foundation of how every model we cover in this series, from Perceptron to SVM to knife bias, make its decision. They all learn this weight automatically from data, and that's exactly what we are building together in this series. Here is a simple look at how Perceptron learn. It starts with a random line, then update its weight every time it make a mistake. Over time, that line move and rotate to separate the two classes correctly. This animation show learning step by step, not all at once, which make the training process easy to understand. Now let's take a look at support vector machine. It doesn't just find any separating line. It look for the one with the largest margin between the two classes. The point closest to the boundaries are called support vector. They are the most important one. This make SVM strong when the classes are clearly separatable and you want a clean robust boundary. Next is logical regression. Even though the name says regression, it really uses for classification. Instead of only drawing the line, it gives us a probability for each classes, so we can see how confident the model is. That make it very useful when you want both a prediction and a sense of clarity. Now here is a decision tree. It works like a flow of simple questions, splitting the data step by step until it reaches a final decision. Each split makes the group more organized and easy to classify. It's one of the most intuitive model because you can actually follow the path it takes. Finally, naive bias. This model uses probability to decide which class is most likely. It make a simple assumption that feature act independently, but even with that assumption, it often works surprisingly well. It's fast, lightweight, and especially useful for text classification and other high dimension data. Now let's our hands-on experiment. So first I'm gonna show you how to download a database. Just follow this website. If you see, this is the very great website for downloading any database. I believe everything is free. So you can search a database or what you can search what type of database we need. So we need a spam. So if I just search, we found a SMS spam collection. Now, once we have that one, we can just click on download and it would download it. So here are a few things like the collection of something like 400 and above spam message were manually extracted from the website, from which location. We can learn more about the data set that we have. Okay, so we would be using the same data set for all the 5 ML problem that we are trying to solve. So once you downloaded your dataset and import it in your Jupyter notebook, you can see it something like this. The first line you can see over here is a ham, and then it will go like some subject lines. And if it's a spam, then it's written. So we can clearly see after the first word, it has written a message. So it's something in a text, but we would try to convert this dataset into the CSV file first. It doesn't even need it, but I'm just gonna explain you like if you are downloading other data set and it's in the CSV format, how you would use it. Like generally we use Panda. So let me show you first how we convert it. So I have already written the code for it. So first we need a panda. So if you have followed my previous videos where we learn how to install Jupyter Notebook and other Python libraries. So if you haven't watched, you can just go to my channel and see it. The previous videos to set up, I've explained in depth. If not, that's all right. If you already have set up, we can study from there. So you have seen the panda, we have panda, and we have file of row file. So I've written the row file name and what the CSV file name I expected, the output file, I would say. These are in the same folder I'm running it. I have written the data. You can see the data variable. And then what we are doing, we are reading the file. So where the tab is, it will just gonna separate into two. One would be the label, another would be the message. And then we are like giving no headers. We don't want to give it anything. And we are just naming it like label and message. Once we have, now we are saving it to the CSV file format. Once you run this block, you would have something like this. I believe I can do this. Yeah. Okay. So you can see it clearly. It has one side is a label, another side is message. I'm just improving the font size so you can see it clearly. So let's try to run a Perceptron. So first we need to import few libraries. So we are importing NumPy, Pandas, and Scikit-learn. From the Scikit-learn, we are importing train test split because we need to split into 80-20 ratio or 70-30 if you want. I prefer 80-20 because it gave more accuracy, but some people go with the 75-25, just sweet spot. So then we are importing another count vectorizer. I would explain it once we are done. It's something like how do machine learning know particular word is something. So computer doesn't understand the word. If I've written like this is my name, it doesn't understand what is this text. It has to convert the text into the number. It's nothing big, it's very simple. But let's skip it for the last part. We have counter vector, then we have a model perceptron, and then we have an accuracy score we are getting from the scikit-learn. Scikit-learn is like very great library. In the first step, we are loading CSV model. For the CSV part, that the data that we have, we are reading from the SMS spam that we just file created, and then we are just printing the first few line to see what are random file data that we have. Then we are distributing into the classes like the label and message. It would understand like ham versus spam. We are labeling it in the second step and convert the text into numeric feature. That's the one I talk about, the count vectorizer. We are providing the message into the count because we don't need for a label, because for the label we have clearly defined 0 or 1. Perceptron is binary classification. That's what we discussed before. For the message part, it would like fit into that. Now the main part is training and testing. Training is like 80, testing is like a 20. It has like text. The test size you see is the exactly what we are telling it to do. Then there is a perceptron, the maximum iteration it need to do, random state. We are just keeping it the default values for now. Now we are fitting the fit part. Here is where exactly happening the training and pasting. So when it's done, we are doing like prediction, like we are providing the test data. We previously removed 20% for testing part. Now we are feeding those for the evaluation. We are gonna see how much total sample it has and the accuracy. We are just multiply with the 100 because generally is give value 0 point something. Here is an output. The total row is CSV 5572 in the data set. Then it has 5 random lines that we printed. Then the classes that we had, like how many ham we had and how many spam we had. Then the total test sample we had 1105. Okay, that's something like 20% of 5000 something for 4800. The misclassified sample are only 34. The accuracy is 96.95. Now let's go with the SVM. So for the SVM, we are using almost identical code. We will have some importing with the NumPy, Pandas, but from the scikit-learn, we are importing linear SVC. Okay. Now the same thing would happen. We are like loading CSV file. We are distributing it, and then we are using random state, and the same code is there. Just the accuracy would change. So over here, once you have run it, the accuracy is 97.93, which is much better than the Perceptron. Okay, on this data set particularly. Now we are going to write the same code for the logistic regression. For the logistic regression, we have SMS spam detection. So for the logistic part, we would also have the same code. The entire code is same. We are just changing the few things. So from the scikit-learn, we are importing the logistic regression, and the same first we would load the CSV file. Then we are converting the labels from the text. Then we are converting text message to numerical features. Then we are splitting into training and testing part. Then we are providing a logistic regression model iteration that we don't want like so many, and then we are providing fit into x and y. So once you evaluate that, it would have the accuracy of 97.57, somewhat logistic. So it's great because we had a small data set. I believe that's why the accuracy are like much better. But if we have large, then I think all accuracy would change. I don't know. Now let's write for the decision tree. As I said, the code would be the same entire same. We are importing numpy, pandas. For from the scikit, we are only importing the decision tree classifier, which is the only difference. And then we are writing the exact same code, like we are importing in CSV. We are converting text message to numerical, then train test, then it evaluates. So we can see the values over here. You can see it has the accuracy of 96.68. Is much better than Perceptron, but not better than the other one, Logistic Regression. Then naive bias on that. So we are using the same data set with that. We are importing the multi-nominal NB. That's its name. The every code almost identical. We are not changing anything. Just for the naive bias model training part, we are just creating variable and then fitting the data into that. The same we did with the other. Once it trained, we are going into the for the evaluation, and you can see how many total it has. So over here you can see it has the accuracy of 97.93, highest in all those. Now here is the main part. In the beginning, I told that the computer, the LLM doesn't understand the text, it only understands the numbers. So over here what it does, it convert your text into the number. So how it does, so over here I've explained with the counter vectorization. So here is the code from scikit-learn. We are importing counter vectorize, the first thing, and then panda. I'm giving you like hello, how are you, then there's a spam, win money now, and there is a ham, are you coming now. So how it does work, first we are creating a vectorize. We have to give fit the text into that, then it will create a vocabulary. The Perceptron is the grandfather of modern AI. It asks one simple question, yes or no. So this create a question, how does it work? So let me exemplify it. So take the input features like amount is $50, The location is in US and time is like 3 a.m. Now the next step is multiply each feature by a weight, amount into weight, location into weight, time into weight. Then it would make a score. In the last step, we are gonna check if the score is greater than 0, then yes. If it's lower than 0, like -1, then it's no. Visualize example. Credit card theft. Your credit card just made a transaction. The transaction amount is $500. The location is Nigeria, unusual. The time is 4 a.m. and the device is with the new phone. The Perceptron analyze score, weight into 500, weight 2 into Nigeria, weight 3 into 4 a.m. and weight into new device plus bias. Now the score would be 101. So that's more than 0. Fraud detection +1. Transaction would be blocked. Training. How AI learns. The learning process, the perceptron doesn't know the right weight yet. It starts with the random weight and learn by try and error. Initial state weight would have like 4 random guesses, for example. And B, the bias is 0 right now. Now, in the training room, the first iteration, let's take an example. The sample is like $100 transaction in the US 2 a.m. with the old device. And that's something normal expected. So the expectation is normal and should be +1. But the prediction is fraud -1, which is wrong. The weight are adjusted now. Then it would try the same calculation again where it update the learning rate, correct the answer and input features. So now the weight value would be 0.15 to 15, and then that's how the weight is being updated each and every time. Now let's take another iteration. In the sample, if 500 is the amount Nigeria 4 a.m. new device, then that should be a fraud, should be -1. Normal +1. If it has detected, then the wrong. Then again the weight get adjusted. Now in the third iteration, the amount is $50 US 10 a.m. old device. Expected normal should be +1. Then make a prediction +1, and that's correct. No adjustment needed. Move to the next sample. And this repeat until the perceptron correctly classified all training examples. What actually happening? Let's visualize. Imagine all transactions are plotted on the graph. So we can clearly draw a best fit line that can separate into two classes: red, the fraud, and blue, the normal one. So in the training, the first round, the line is tilted wrong. In the second round, line is tilted a bit. Then on the third round, line slides down, and on the fourth and last the line get steeper until it perfectly separate blue from red. That is decision boundary. The point above it +1, the fraud one, and the points below it -1, the normal one. Now the key property, so the strengths are fast, simple, adaptive and online, but it has few weaknesses like forget, linear only, no probabilities, sensitive to outliners. One weird point can ruin the boundary. So when does it fail? So the data might look like this. No straight line can separate them. The perceptron gets stuck in a loop and never converging. Remember the perceptron? It found any line that separate two classes. The SVM is picker. It does not want just a line, it want the best line. So perceptron might ask, does this line work? And SVM is like, is this the most confident line? There are infinite way to draw separate lines. So first option that we have like separating like this, another option that we have separating like this, and the last the best option would be separating with the two lines. Then all three separate the classes, but which one is the best for the new unseen data? The answer is option C, the line with the widest margin. So that clearly create a question, what is margin? The margin is a street between the closest blue and the red point. Let's visualize. So the top boundary line touching the red one and top bottom line touching the blue one. And that will be the center street line, that's called decision line. The SVM goal is to maximize this gap. Why? Because a wider margin means more robust to noise, less sensitive to outliners, better generalization to new data. Real world analogy, you are building a highway between two cities. You could build it right next to the house, risky, or you could give yourself a wide buffer, safe. The SVM picked the safest route. The point that touch the margin boundaries are called support vectors. Visualize the support vectors are the above sitting on the boundary, the regular point far from the boundaries, and these are the margin. So why are they special? They define the boundary. They are critical points. Moving any other point, the line doesn't care. For example, imagine the decision line is set. If you drag a red point that's far and the line the same, you drag a red point on the boundary, the line jump. That's why it's called support vector. They support the decision line position. SVM solve an optimization problem. The first weight that make the margin as wide as possible while keeping all the points on the correct side of the line. Real world example is image recognition. So you all thought the same. Self-driving car, pedestrian and the tree. Featuring like a edge sharpness, vertical symmetry, skin color probability, shape circularity. The training data is like a with the pedestrian it has something kind of arrays, and with the trees it has some arrays. Now SVM find the optimum boundaries in the 4D space. So the decision boundary would have something kind of this formula. The new image comes in features with the this, and the score would be something 8.2, 7.9, 9.9, 3.9, and that will create 165.31 something. So if it's like something bigger than zero, the pedestrian detected. Why margin matter? A pedestrian at the edge of the shadow might shift features value slightly. The wide margin protect against this small shift. What if data isn't linearly separable? Sometimes no straight line can separate the classes. So for instance, we have some original data like this. Some of them are on the left side and few are on the right. No single straight line can work. But here is a trick. Lift it from the higher dimensional, the kernel trick. Instead of working in 2D, imagine lifting each point into 3D space using a transformation function. So before we had something like this, now a plane can separate them. So this is the plane you can see on the screen. There is a Z, there is a X, and this is the like 3D separating between the spaces. This is called a kernel trick. You don't actually compute the high dimensional transformation. The kernel function does it implicitly. Real data has a outliners and noise. Sometimes it's better to allow a few mistakes rather than twist the boundaries to fit every single points. That's called soft margin. Visualize, we have like hard tolerance and we are just leaving it to the soft tolerance. So what are the strengths? I would say the optimal margin is like the most confidence boundary. Then there is a kernel tricks. There is a robust, work in high dimensional, great for text and images, principled. So there are few drawbacks. I would say weaknesses. The slow and large data sets. Memory is intensive, like it stores all the support vectors. Parameter turning. Probabilistic output. Binary by default. So when should I use SVM? There is a small to medium data set that we have less than 100,000 samples. It is a complex, non-linear boundaries needed. High dimensional data, text, images. You need a confidence, interpretable boundaries. Computational resources are not constrained. Where we can't use it now. The massive data set need more probability estimates. Want an online learning algorithm. Dataset is imbalanced and you can't tune it carefully. Logistic regression. Despite the word regression, this is a classifier. It does not predict number, it predicts probabilities. Perceptron is like yes or no. SVM is like yes or no with confidence. Logistic regression is like there is a 87% chance it is yes. That's the magic. So how does that work? It still draw a straight line between the features, just like Perceptron and SVM, but instead of saying left is 0, right is 1. It turn linear score into probability between 0 and 1. So compounding a linear score same as before, passing it through sigmoid function, result is always between 0 and 1. Let's see something about sigmoid. So sigmoid has this formula. What different value do? So if we change the value of sigmoid, then it changes the value of probability. We can see it over here on the screen. The decision threshold usually we pick is zero point 0.5. Real world example. Predict the probability of patient has a heart disease. So it might has a feature like age, blood pressure, cholesterol level, smoking, exercise frequency. So we are putting all in a training data. Then the model learn the weight. It adjusts the weight and for each and every parameter. Now when the new patients arrive, it just see the data, and from the data it can make a prediction. So for instance, it has done like 3.79, then the decision would be the 97.8% chance of heart disease. The output is just not yes, but it a rescore that doctor can use. So logistic regression use maximum likelihood estimation. It try to find weight that make observed data as probable as possible. For each training example, it calculate the actual label, loss, and if actual label is 0, then minus log the total loss in the sum of all these, then it goes to gradient descent to maximize the losses. Unlike Perceptron, which only update the mistakes, logistic regression update on every example, nudging probabilities gently. What are the strengths and weaknesses? So I would say it gives probability, fast and simple, interpretable, works well when relationship is roughly linear, calibrated. There's some weaknesses. It make an assumption, can't capture complex nonlinear pattern, sensitive to outliners and require a feature to scaling its best result. So when to use logistic regression? You need a probability output. You want something fast, interpretable. Data set is like medium size, baseline model before the complex algorithm. The fun fact is, it is originally developed in 1830 by Piers Franco to model population growth, not email or disease. Forget the complex math for a second. Decision tree exactly work like a games of 20 question. It look at your data and ask a series of yes and no question to narrow down the answer. Is the person above 80? Do they have a job? Is their credit score is 700? By the time it finishes asking, it has categorized your data. How it's structured? Imagine an upside down tree. So very first would be the question, and that would be the answer yes and no. Then the final answer might be, if there is some category for the yes, then it would just create another nodes, and this would be go into loop until it finally found the node. So there is a terminology called like a root node, the top level. The internal node is a question, the leaf node is the final destination. The branches are yes and no path. How does the tree know which question to ask first? It want to reduce disordered. Imagine a jar of mix of candy. It's messy, high entropy. The tree asks, is the candy is red? The result would be pure jar 1 and jar 2. The tree always pick the question that create the purest group. Let's take an example. Will the bank give you a loan or not? The tree analyze 1,000 past customer. The question one is like a question. It is like income is 50K or not. So if you have an income which is like a $50,000, then if it's yes or no, if it's no, then the leaf goes to with the 80% accuracy and say it's rejected. Now, if you're on the yes side, then there will be then a question: is your credit score is like a 650 or above? If lease is say like a no, then it's rejected with 95% accuracy. Then it will, if it's yes, then it will go to the question three. Now the question three is debt to income ratio. If he has a debt, then it would be with the 70% accuracy, it's file rejected. Or if it has yes, then it would be approved. So it has like a very big weakness, like overfitting. A decision tree is too good at its job. If you let it, it will ask 1,000 questions to perfectly fit every single point in your training data. So in a training data, we have the perfect 100% correct answer, but in the real world, it's terrible. It always fail. This is like a student memorizing the textbook instead of understanding the concept. If the question changes slightly, they fail. How to fix it? pruning. We cut the tree short. We tell it stop asking question after depth 5. So it has some strains like easy to explain, no scaling needed, handle categories, and capture known linearity, which is like great. It can handle complex shapes. So for the weakness part, it has like a very big issue of overfitting, unstable, greedy. It makes like best choice now, but misses a better choice later. When to use decision tree, you need to explain the why to a human boss. You have mixed data, numbers, and text. You want a quick baseline model. Let's go to the native bias. Imagine you are a detective at a crime scene. You find a clue, a footprint, a hair strand, a fingerprint. Native bias asks, given the clues, who is the most likely the culprit? It uses pure probability to answer. No line, no margin, no tree, just the math that's been around 300 years. It's based on Bayes' theorem for the 18th century. This is the formula. So if I translate that into plain English, then there is a P A slash B probability of A given a B happen. Now probability of B given a happen. Probability of A happening at all. Probability of B happening at all. So the real version is like P disease symptoms and equal to P symptoms disease into P disease. The knife base assume every feature is independent. Example, if it's a spam, the word free has no relationship to the word money. If it's cat, the tail length has no relationship to its fur color. We know this is wrong in real life. Free and money often appear together in the spam. Cat with a long tail often have a different fur pattern. But here is a shocking truth. Even with this wrong assumption, naive bias work incredibly well. Why? It only care about the ranking of probabilities, not exact values. Even with the wrong number, the relationship orders stay correct. It's like taking a slightly blurred photo, you can still recognize the face. Your email arrives, naive bias check the keyword. The word is like free winner meeting. The first step is to calculate the probability if it's spam. So it do 30% of all emails prior. So from that, the 80% free, 60% winner, 10% is a meeting. So it create into the formula, calculate the probability, and it's a ham, not a spam. The ham is 70% of all email priority. So it has like a free winner meetings 5 to 40. Then it do the calculation. Now it compare spam score and ham score. Spam score is 51 times higher. Flag as a spam. Not all data is the same. Naive bias has a three version. Gaussian naive bias, you use the data is continuous number. For example, height, weight, temperature. The data follow a bell curve normal distribution. The multinomial naive bias. The data is count, word frequencies in a document, text classification or spam detection. The third one is Bernoulli naive bias. You use when data is binary. Did the word X appear? Yes or no? Short document, present only features. So let's take an example, positive or negative. The customer has this. This product is amazing and wonderful. So the prior probabilities are 50% positive and 50% would be the negative. So the likelihood learned from a training data has this table can see on the screen. Now, first it calculate the positive scores. So it would multiply the all the values from the positive field, and then it would multiply all the values from the negative in the fourth step. So we now have two values. Now it would compare like which one is like how much higher than the positive. Positive score is like thousands of times higher than the it has detected the positive sentimental detection. That's how it works. So it has one problem, the zero problem. The word will never appear in your training data. The quantum spam is zero. If any single probability is zero, the whole product becomes a zero. Even the 99 other clues point to the spam, one zero kill the prediction. How do we solve it? Instead of like multiplying with a zero, we just add a small number with everything where we have like given the unknown a tiny non-zero probability instead of zero. Let's talk about the advantages. It is lightning fast, handle high dimensional data, little data needed, probabilistic is very great, great for the text. So it has some drawbacks. The native assumptions, rarely true independent, zero probability, not great with the corrected features, and can't learn interactions. So when you use a naive bias, you might be using for a text classification, real-time prediction, small data set where the neural network can't train, baseline to beat with the more complex model. When not to use, features are like highly corrected. You probably need to capture interaction. You probably estimate need to be separate. All right, so let's take a look at over here. I have imported two different data set and train our five basic classification algorithm on that. So first, I'm just importing warning to ignore the warnings printed on the terminal. Then over here, I'm just importing few libraries, NumPy, Matplotlib to scatter it and handling the CSV dataset from the scikit-learn. First, we are importing the dataset that the breast cancer and the wine one. Then we wanted a train test split. Then from that we want a standard scaler, then accuracy scorer. Then we are importing PCA. Then we are importing Perceptron, Logistic Regression, Support Vector Machine, Decision Tree Classifier, and Gaussian Naive Bias. So we have a test size 0.2, which is 80% for training and 20% for the testing one. We have the two data sets, so just we are loading and separating the data set over here. Then from the standardized linear for the SVM and for the PCA, we are just for the visualization part, we are just creating transformation. Okay, we are just importing the data set. Then over here you can see how many lines of code that we have. It's pretty small, but we should be good. So we already imported our data set for the perceptron and we need to train it. So for the train on the cancer part, I have written this code, and for the wine part, this is the code. Now we are gonna just see the accuracy once it's completed training, and we are providing the testing data, then the accuracy score. So for the visualization part, I've written this code. It's nothing, just how I want to annotate few things. So over here you can see the perceptron accuracy is 0.96 for the breast cancer, and for the wine accuracy is 0.94. And over here you can see it has clearly identified so many different data sets. So for the SVM training dataset visualization, for the support vector machine, I would be writing the same code, just having few data here and there, the variable names change, and we are doing the same. We are providing the testing, then we are seeing the accuracy. Same with the wine, and we are gonna just print on the terminal. Then we are using the matplotlib for plotting it on the graph. So over here you can see for the breast cancer it has the accuracy of 97, and for the wine it's 94. So it has also identified clearly. Now move it to logistic regression part. So remember that do on the probability, so that's why it might has a different accuracy than the previous ones. So over here, if there is a breast cancer and wine accuracy, we are printing it over here, doing the plotting, the same thing. It has the accuracy of 98 and 97, which is much higher than the before we have seen. So on the probability, we don't see it like two parts that we used to see in different one, because it is not like binary classification. It is mostly on probabilistic. That's why you see how many it has predicted, how much where it went wrong. So over here you can see for the wine they have different data sets. So now move to the tree one. So for the decision tree, we are writing the same code for splitting the data, then providing testing, then the fitting into that, then we are predicting it, then we are testing the accuracy. For the wine we are doing the same, then we would be doing the same thing. So let's see, for the breast cancer accuracy is 0.94, and for the wine is 0.94. So they are pretty much the same. I don't see any difference, but it is also a good algorithm for the naive bias training dataset and visualization. So we would be doing the same Gaussian NB, we are using it. Then we are using the wine. There is a breast cancer. Okay, all right. So over here, let's move it to the printed part. So for the naive bias, breast cancer accuracy is 0.93, but wine is much higher, 0.97. So over here, you can see the clear difference. But we have seen all the five. We haven't compared those So now what we are going to do, we are just going to compare each and every individual one. So we already have a data, so we just need to do the comparison chart. So over here, Perceptron accuracy, SVM, logistic regression, decision tree, and naive bias. So over here we can see which one is much better on a breast cancer and on the wine. So we have a clear winner over here for the breast cancer, and I see the tie between naive bias and logistic regression. All right, that's tour of our 5 fundamental machine learning algorithm, all tested on the same database, so you could see that strain side by side. If you want to go deeper, you can take exact code database from this video, work parameters, and see how the decision boundaries and accuracy change on your own machine. In the next video, we will check those ideas into ensemble and more advanced models. But this everything start with what you have just seen. Thanks for spending your time learning with me. If this helped clarify a few things, feel free to rewatch the section, do experiment, and then I will see you in the next one. Thank you.